Hello and welcome to the MOOC on optical communications. In this short module, we are going to discuss dispersion induced limitations. We have already looked at dispersion induced limitation in the optical communication systems earlier, because when you have a fiber which has a certain amount of dispersion, its immediate effect is to cause pulse spreading. So, you might transmit a pulse in a certain time slot. After that pulse, you want to transmit another pulse carrying the information. However, when you transmit these pulses through the optical fiber, because of dispersion, the pulses will spread and go beyond their initial time slots and start to talk to each other. Okay, so there is this crosstalk which we denote by this phenomenon called intersymbol interference. One symbol tries to interfere the other symbol because the pulse actually spreads beyond its initial time slot. Okay. So, this dispersion in a standard single mode fiber occurs because of the fiber dispersion, which we have already seen to be coming from material dispersion as well as the waveguide dispersion. Both these dispersions are functions of wavelength, and because when you modulate a certain carrier and transmit it through the fiber, the modulated data occupies a certain amount of spectrum, and this spectrum basically influences the overall dispersion, because that spectrum will not be non-zero if you want to transmit any modulation. In time domain, we can start to think of the transmitted electric field, okay, whose amplitude, if we denote it by u and at say at z equal to 0, can be described as having a Gaussian amplitude. Okay. Although in practice the pulses are not really Gaussian, but more or less this type of a pulse shaping that we normally use in the on-off keying systems, it is still okay to consider Gaussian because they are quite easy to work with to get some analytical ideas or analytical formulas to help us understand how dispersion affects the system. So, assuming that this is a Gaussian pulse shape, we can write this as exponential minus t square by 2 t0 square. We will now assume that there is no loss in the optical fiber. Okay. So, earlier we looked at the cases where loss was the major factor. Now we are going to assume that there are no losses in the fiber, and whatever that we obtain limitation is simply because of the chromatic dispersion. Okay. Of course, we are considering single mode fibers, therefore, that is the only dispersion that we are interested in. Okay. We are not interested in the multimode dispersion induced in the multimode fibers. There is some amplitude to this electric field, which you can write this as A in. This is inconsequential because we are assuming no loss of amplitude in the system, but more importantly, and this is the one that is important, you actually have the initial pulse width given by T0. So, if you sketch this as a function of time, you will see that at time t equal to 0 you have an amplitude of A in, and then you basically have this sort of a distribution, right. The width of this in terms of the FWHM, that is the first width at half maximum when the amplitude has actually decayed to half, is given by around roughly 1.665 times T0. So, this is the optical pulse that is actually launched. Of course, what you launch is a sequence of optical pulses. Here the bit is 1, bit is 0, bit is 1. Sometimes right after the first bit you are going to get a 1 here, indicating that these two time slots, which are very close and characterized by having the same bit, are more likely to suffer from intersymbol interference than these two bits, because this can be allowed to expand a little bit. What dispersion does is to expand the pulses around here, but when you expand these pulses, you will see that the two start to merge together, and the overall pulse shape that you expect out of this bit sequence looks something like this. Okay. So, clearly these two are much more strongly influenced. This is also getting influenced because if you, for example, have a threshold somewhere here, then you can see that because of the pulse spreading from the previous slot and the pulse spreading from the next slot and probably the other slot is now adding up to increase the overall amplitude when the bit is 0. So, sometimes if this pulse envelope reaches above the threshold, then even this bit will be in error. In fact, you normally define the intersymbol interference or model the intersymbol interference by a certain memory length, indicating that minus m of the previous slots, that is previous m slots to the next m slots time slots are the ones which are interfering in the present slot. Okay, you can think of this entire thing as a finite impulse response filter with appropriate set of coefficients in order to model this, and this FIR filter model of the dispersion depends on what is the dispersion coefficient. The larger the value of D, the larger will be the value of the time slots which are actually talking to each other. Okay, anyway, so we have launched this optical power or this optical pulses into the fiber, and what happens as they propagate through the fiber is something that we have already looked at. We see that the amplitude decreases, okay, because of the dispersion, but more importantly your pulse time or the pulse duration actually spreads, because after propagating a distance z equal to L, the pulse width will now be dependent on the beta of the or the dispersion coefficient of the fiber. D is related to beta 2 as we have discussed in the previous module. So you have beta 2 square L square. Okay. So in some sense beta 2 into L is the effective or is the additional spreading that you are going to get. Normalize, divide this one by T0 square would be the actual TL square. The FWHM here after Z equal to L is of course given by 1.665 TL. So if you look at the FWHM at Z equal to L over FWHM at Z equal to 0, this would be equal to TL by T0, right? And because TL is greater than T0, the FWHM at Z by L will be greater than FWHM at Z equal to L. Okay. Now you can't of course start to choose T0 to be very small, because if you choose T0 to be small, then TL square being inversely proportional to T0 square will increase, leading to a problem. You can't choose TL too large as well, because you might simply get a situation from the numerator that T04 is larger than beta 2 square into L square. Okay. And if you put in these conditions, you will see that T0 too large will lead to TL square, which is approximately T0 square, which anyway will limit the data rate. Okay. So you can't choose T0 too small or T0 too large. What you do in practice, or at least in this problem, is to find out what is the optimum length for the given value. Okay. So you can do this optimum length by differentiating TL with respect to T0 and setting the result to 0. If you do this, you find that the optimum value for the initial choice of the pulse is given by the fiber and the length of propagation. Now this is very crucial. You actually have a length of propagation which is determining the optimum pulse width. Okay. So this optimum pulse width, if you were to choose, then the root mean square width of the Gaussian pulse, which is the way in which we normally talk about the width of the optical pulses, is actually given by T0 by square root 2. Okay. So this can be related to the width of the Gaussian pulse at Z equal to 0. Okay. And the same RMS width at Z equal to L will be given by TL by root 2. Okay. It is a slightly different way of calculating. This one is rather easier, because a general Gaussian random variable is given by 1 by sigma square root 2 pi exponential minus x square by 2 sigma square, and this sigma is essentially the root mean square width that we are looking at, and therefore this is kind of easier to deal with in that particular case. Okay. So what you get is the width, the RMS width. This is not the short noise variance that we were looking for. This is the RMS width after propagating a distance Z equal to L, can be written as 4 sigma to the power 4 plus beta 2 square L square divided by 4 sigma 0 square. What we have done is to simply replace TL and T0 in this expression by the corresponding variables of sigma L. For ISI to be manageable, okay, of course nothing is great that ISI should actually be equal to 0, but in case you cannot hope to get a 0, to manage the ISI, the necessary requirement that is commonly used is that the pulse spreading, okay, after propagating a certain distance L has to be less than the bit period by 4. That is, you are allowed about a 12.5% spreading onto the right hand side and 12.5% spreading onto the left hand side. That is, your pulse can spread 12.5% to the next slot and 12.5% to the previous slot. So this sort of a 25% spreading is what we are allowed to have. This is a criteria that is commonly used. This is the criterion that is commonly used in practice. Okay. So, you have a 25% pulse spreading allowed, and if you substitute that condition onto this one and rearrange the equation, what you get, and remember also that TB is inversely proportional to B as 1 by 2 TB, therefore TB is given by 1 by 2B. Okay. So, because of this relationship, you can then take a look at what will happen to sigma L and sigma, in terms of sigma L and B. So, you get 4 sigma to the power 4 plus beta 2 square L square divided by 4 sigma square, which as we know is sigma L square, which we have just written down in the top. So, this to the power half, because you are looking at sigma into B. So, this one should be times B should be less than or equal to 1 by 4. Okay. So, if you assume that this would be the condition and substitute for the optimum value of sigma 0, which will be given by square root of beta 2 L by 2. Remember, the optimum T0 value was given by square root of beta 2 L, and sigma is related to T0 by square root of 2. So, with that you can see that the optimum sigma 0, the initial RMS pulse width, must be of this nature, and when this is the case, you can simplify the relationship slightly here and write this as beta into beta 2 L under root should be less than or equal to 1 by 4. Okay. If you fix beta 2, right, then what will happen? If you fix beta 2, then the bit as the transmission distance L increases, the product B into square root L will increase only as square root L. Okay. So, the transmission distance, or if you were to now fix B, then the transmission actually decreases by 1 by square root L. So, as the length increases linearly, the transmission performance or the maximum transmission distance only increases or decreases by a factor of 1 by square root L. What can we do in order to combat this ISI in practice? There are a lot of techniques that are used. For most legacy systems, okay, wherein you do not have any dispersion compensation, then so the transmitter and receiver are just linked by a standard single mode fiber, you simply apply electronic dispersion compensation at the output end, that is at the receiver end, in order to compensate dispersion. Many dispersion systems are actually managed by dispersion managed systems. So, in order to do dispersion management, you have two options. Okay. What you do is you take the single mode fiber, and after one span, after where you have to reshape the signals, you put a dispersion compensating fiber. The dispersion compensating fiber will have a minus beta 2, okay, which will be in magnitude different from the plus beta 2 that you have for the standard single mode fiber. But if you choose the length of the DCF appropriately and the length of the standard single mode fiber appropriately, then you can completely cancel dispersion at the end of the span. Okay. The other way would be to actually let the single mode fiber be completely replaced by a dispersion shifted fiber, okay, wherein and then operate everything at the 0 dispersion wavelength. Okay. So, if you operate transmission system at 0 dispersion wavelength, then the impact of dispersion can be minimized. Okay. These are some simple ways in which we have talked about. The actual application will involve a properly detailed way in which the dispersion changes over the fiber that is installed, and the nature of the nature of the DCF that you have, and how do you actually connect them together. Okay. So, that is something that is slightly beyond the scope of the course here. So, we will stop at this point and note what we have done. We have looked at in the earlier module what happens when your loss is the major factor that limits your performance, and then you come to the dispersion case, which again is related to the length of the fiber. Although the effect of fiber dispersion will scale as 1 by square root of L, the effect of length will show up in terms of the degraded BER performance of the systems. Thank you very much.